So good morning, everyone. My name is Sean Finan. I'm the CEO of the Irish Bioenergy Association, and I'm delighted to host this morning's webinar. This morning, we will discuss the topic of next generation anaerobic digestion, dual stage hydrolysis, and beyond, where Clinty Bio will outline their company and the services that they provide and products that they provide. Just before we go into our webinar, just a brief introduction to our agenda for this morning. I will give an introduction to the Irish Bioenergy Association. As I said, we will then hear presentations from Clinty Bio representatives. We will have a very short panel discussion followed by a Q&A session, and we encourage all attendees to submit questions through the Q&A tab at the bottom of the screen. We will endeavour to answer as many of your questions as possible, and if there's any questions that we need to follow up with after, we will also do that. So by way of introduction, the Irish Bioenergy Association, for any of our attendees this morning who are not familiar with the association, it was established in 1999. We work as the representative body and organisation for the Irish bioenergy industry. We cover the island of Ireland, where we have members in both Northern Ireland and the Republic of Ireland. And our sectors include solid biomass, biogas, biomethane, biofuels, biochar, wood fuels, and energy crops. Our main work is in the area of policy, lobbying and advocacy, knowledge transfer, and our membership is broad and diverse, which includes farmers, foresters, SME companies, technology providers, consultants, and a wide variety of other interested parties in the bioenergy sector. Up to 250 individuals, SME, corporate, and headline members. And if you'd like to discuss membership with us or become a member if you're not already a member, please feel free to get in touch with us afterwards. We also roll out a number of research and development projects, including Interreg Cascade Northwest Europe project, and we also administer and manage the Wood Fuel Quality Assurance Scheme, and further information is available on our website. We are externally affiliated to Bioenergy Europe, the European Biogas Association, and a founding member of Renewable Energy Ireland. So moving on, this is our webinar number 49. We have had a few webinars this year. It has been more infrequent this year, but all our webinars are available on the IrBEA YouTube channel. So please feel free to look on the YouTube channel if you would like to view the recordings of any of the webinars which have taken place to date. They've covered a wide variety of topics and speakers and companies over the last number of years. Next up is our fact sheet series. So we have a fact sheet series, and this has been expanded and developed. So again, they're available for anyone that would like to view them. And we also have a number of sector reports and publications, which again are available on our website for anyone that wants to view them. So introducing Clinty Bio and the topic this morning. So Clinty Bio representatives will present on the company, the products and services they provide. So our topic is optimizing anaerobic digestion performance through data-driven biological support, pilot scale testing, and dual stage hydrolysis technology. An introduction to Clinty's managed service model. This will be followed by real world case studies showcasing how ongoing biological monitoring and optimization have delivered measurable improvements in AD stability and gas yield. So it's quite a technical topic this morning. We don't usually go into such technical detail on these webinars, but we are open to that for any other potential participants or presenters that would like to showcase their product and solution. The presenters will share their insights from their 60-litre pilot lane digester, where customer-specified feedstock scenarios are tested to de-risk investments and inform full-scale design. And a case study of recently completed full-scale dual-stage hydrolysis project in Ireland will be showcased, highlighting results, learnings, and practical outcomes. And I'm delighted to introduce our speakers this morning. So Mile Wilford. Mile is the General Manager of Clinty Bio, which is a diverse group of companies spanning biological solutions, laboratory services, water treatment technologies, resource recovery, and chemical manufacturing. And he oversees the group's strategy, operational performance, and commercial development, with a strong emphasis on enhancing the organization's scientific, analytic, and biological innovation. A key part of Miles' role is leading Clinty Bio, where they've developed a pioneering biological solutions division, and it's Miles' leadership is grounded in nearly 2 decades of experience across environmental management, business improvement, and senior operational roles within food production, environmental, and process industries. His earlier career involved environmental consultancy, operational management, improvement roles at Linden Foods, followed by commercial and strategic leadership positions within the Clinty Group. So we're delighted that Mile can join us this morning and present this morning. Our next speaker is Wade McRoberts. Wade is the Technical Director at Clinty Bio. He is also a specialist in biological waste to energy systems with over a decade of experience advancing anaerobic digestion, modeling, diagnostic, and operator training. As the founder of ALPS Euroscience UK, Wade has played a central role in shaping a modern data-driven approach to AD performance management, and he is recognized for transforming complex process behavior into clear, visual, and actionable tool development, modular dashboards, composite performance indices, and scenario modeling frameworks that support reliable decision-making, risk management, and operational optimization. So we're delighted again, Wade, to have you with us this morning. And our third speaker is Dara Buckley. Dara is a molecular biologist, a biological engineer and microbiologist with experience spanning cancer research, inflammation biology, food and beverage microbiology. He completed an MSc in molecular biology and biotechnology at Queen's University of Belfast in 2016, and in 2017 he joined the Clinical Cancer Research Trust at the Conway Institute, UCD, gaining experience in cancer therapeutic research, including cell culture, drug response studies, and tissue microarray analysis. From 2018 to 23, he worked with Food Health Ireland, and then moved as a microbiologist from 2023 to 2024 to Diageo, and since 2024 Dara has worked as a microbiologist and bioprocess engineer at Clinty Bio, focusing on improving anaerobic digestion efficiency and stabilizing through small-scale technology trials and full-scale plant optimization. So we're delighted to have all our presenters this morning, so I'm not going to stop sharing and ask Dara to share your screen, and I'll leave it to you then to go through your presentation. And again, just a reminder to all our participants while Dara is sharing, if there is anyone, if you have questions, please feel free to share them through the Q&A tab, and we will address them all at the end of our webinar. So over to you. Mile, is it first or Dara?
Sure. Good morning, everybody. Thanks for attending. Thanks, Sean, for the introductions. My name is Mile Wilford. I'm the General Manager of the Clinty Bio and the Clinty Group of companies. We're really excited to tell you about some of the recent developments and a little bit of the background of who we are and why we think we're well placed to help chart Ireland's course or be part of the journey from where we are now to where we would like to be. So from the course you'll hear briefly from me on the introductory side of things. I'll hand over to my colleague Wade, who will talk us through a little bit around the importance of understanding feedstocks, you know, the requirement to start at the start of the process. And then Dara will take us through a couple of sort of recoveries that we've done for AD plants which have encountered problems, and then ultimately through the role and importance of dual stage hydrolysis. So, like I say, we will give you a quick spin through who we are. So, the Clinty Group of companies, we're headquartered in Northern Ireland. We cover, as Sean said, a sort of broad range through from chemical manufacture to aeronautical. We have a liquid activated carbon business, but principally we're here to talk about obviously our biological arm today. But been operating, still privately owned, operating since 1978, manufacturing somewhere in the region of 40,000 tons of chemicals per year in our coagulant business. But as we've grown and expanded and developed, we've we now have a UCAS accredited laboratory headquartered in the Port of Belfast, and we have a fairly extensive biological and chemical engineering team attached to that, which allows us to provide a full range of services to support waste and water treatment and valorization. So what are we? And I guess in principle, we're more than a lab, albeit we have a lab. We have a lab. So it's fundamentally, we talk about analysis with interpretation. And the managed service that we offer is our sort of blue chip offering to AD plants. It's based around the principle of everybody understands the value of having analysis, regular routine analysis conducted on their anaerobic digester. But ultimately, it's making sure that the analysis it's the right parameters tested, and that the results are understood and interpreted. And we'll take you through a great case study of a customer that was, prior to our involvement, was receiving an awful lot of analysis, but didn't have the necessary or didn't have the capacity to interpret that results and understand what it meant. So as a very first thing, what we try to do is link the operator of the AD plant with the laboratory with biological interpretation and hand holding. So as part of that, all our accounts have direct account management, access to our biologists, and then the understanding that comes with years of academic study in the field of biology. And if you look on the next slide there, you'll see an example of one of these dashboards where this is a site, and what we typically work around is this idea of sample, analyze, interpret, and optimize. So these sort of managed service clients that we have, we'll collect a sample on the Monday from the AD plant. It's in our laboratory in Belfast on the Tuesday. It's interpreted or analyzed and interpreted by the close of play on the Friday. So every week, those sites that have availed of this service, they have this dashboard is generated. It's maintained as live as the results roll in, and it tracks the site's performance, the site's biology against these sort of key performance indicators, these key metrics. And it allows us then ultimately to optimize, whether that's identifying potential inhibitory elements and what we can do to mitigate those, and agreeing with the site what those KPIs could be. So for some sites, they want to grow, they have capacity to grow. What can we do to enable that site to generate more gas or higher quality gas? And we have all the engineering space and laboratory skills to identify those. And for others, it's simply, how do we consume less feed and generate the same amount of gas? And again, we have all the necessary capabilities to help that operator determine, based on the recipe that I have, how can I meaningfully reduce my feed and maintain the same engine uptime? So for us, it all starts with, like we said at the start, we're science first. We don't point towards these sort of additives and the enzymes and these additional items. Really, we think the foundations on a successful, viable, long-term feasible AD plant is understanding the biology and managing the feedstock in such a way to enhance the output from the particular site. So Wade will take through shortly the benefits of the feedstocks, and then Dara ultimately will take us through what these dual stage benefits are, and to give you a very sort of potted summary of what we've seen with the benefits of dual stage is it's kind of an either or in the first two. Either you're able to reduce your OPEX because you can produce significantly more gas from a 20 to 30% reduction in your feedstock, or you have the ability to push an awful lot more feedstock through an existing asset. So we've seen, we're saying conservatively 2 times the existing plant capacity. That could potentially be 3 plus times the existing plant capacity. The ability to push the organic loading rate. So you can sweat much more out of the existing asset. Or ultimately, if you were in the throes of designing and building an AD plant, you may find that you can shrink your footprint, shrink your capex, and still generate the same volume of gas. Gas quality, we've seen both at the pilot scale and at the commercial scale. We've seen an increase in methane quality from by 5 to 10%, and a knock-on benefit of hydrogen sulfide numbers dropping certainly below 50, frequently into single figures in the methane tanks. So notable, demonstrable, repeatable improvements in gas quality. The stability then, with dual stage, the separation of the first phases of AD from the methanogenesis stage yields significant protection for the methanogens, and we'll take you through why that is. But ultimately, this the sort of the is it too good to be true? Is there is very, very low risk. You can convert an existing tank if you require, or you're building in effect a very small tank, which ultimately, if it wasn't for you, as it were, you can convert back. But we've yet to see any downsides on rolling out of dual stage anaerobic digestion. So if I hand over to my colleague Wade McRoberts, he will take you through the importance of feedstock characterization at the start of anaerobic digestion.
Thank you, Mal. Sorry, I couldn't find my mouse there. Good morning, all. I'll just go very, very briefly through the importance of feedstock characterization. As I sometimes get a little frustrated with some of the due diligence processes and some of the management of anaerobic digestion. I'll just do this very briefly. So why feedstock characterization is important? It's more than just a lab exercise. It's a strategic tool for stability, optimization, and innovation in anaerobic digestion, and it all starts with the feedstock. What feedstock is available? How does one co-digest it? Without it, we're flying blind. And I'm speaking largely in the context of the Irish market, as it's a fairly new market, and a lot of these sites, I'm sure, are greenfield sites. And I cannot stress the importance of a full feedstock characterization, not just a singular BMP type scenario. The limitations on the singular BMP batch process, whilst they might be useful to inform certain economic models, etc., but they're static snapshots of a dynamic system, and it doesn't give you the full picture of what the potentials are. So whilst they are valuable in terms of understanding individual feedstocks, you're not going to get a full picture in terms of co-digestion and optimization of that co-digestion, because ultimately, at the end of the day, anaerobic digestion is an environmental process by which we are trying to reduce as much volatile solids as we possibly can, and produce gas from that. They also don't account for any kind of microbial adaptation in a system. So again, it's very static, it's not dynamic, and the bugs can adapt to certain conditions, certain feedstocks. They don't account for retention time, and frankly don't account for any kind of inhibitory compounds. We've seen a lot through our work in terms of inhibitory compounds, such as phenolic compounds, etc. So my opinion is a little bit misleading. It gives you a number, and that's pretty much where it is. So what we do at Clinty Bio is we expand that into what we call the biodegradability index. And this index essentially just takes what the true value of the volatile solids and the COD are in the particular feedstock, and we look at that, which would then be able to it reveals how much of the substrate is truly converted if you take your BMP against your theoretical BMP scenario. BI also helps identify the resistant fractions, the recalcitrants within the system. These recalcitrants, such as lignins and fats, certain fats, etc. And again, I use the word dynamic. It provides the dynamic of it. And it's a diagnostic tool that supports realistic yield expectations and ultimately informs process design. So again, in the Irish context, it's very much geared towards that greenfield projects, but it's not necessarily just for greenfield projects. And Dara will take you through a few experiences that we've had in terms of feedstock and how the feedstock adjustment or changes at the front end that are unknown by the operators can result in a complete collapse of the system. And in my experience, I've dealt with a number of those collapses, several of those collapses. Can you just go to the next slide there, please, Dara? So just in closing, and I will hand it over to Dara with the more juicy side of our webinar, but the optimizing decisions that we are able to make with that robust data, we can simulate outcomes, gas yield, digestate quality, and risk indices. We can track early warning indicators like VFA profiles, PFOS ratios, and biodegradability trends. And this ultimately supports the cost-effective, resilient operations and better operator training. But the key message from my very brief discussion here is, in my opinion, feedstock characterization isn't optional. It is a strategic process control and informs not just your economic models, but also your process designs, etc., etc. So thank you. I'll hand you over to Dara, who is going to take you through some of our experiences.
Sure. Thanks, Wade. So as Wade was discussing, I'm going to discuss 4 case studies. The first 2 are to demonstrate the value of the managed service that we offer. 2 plants that faced downtime as a result of acidification, and how the managed service resulted in them coming back better, more efficient, and have since managed service has addressed their problems. They have had no downtime, and everything has gone a lot better. So on the right-hand side here, you'll see an example of a typical data sheet you might receive as an operator who is paying for a lab analysis. Now, if you're not trained in this type of thing, this is all just numbers. You know, what trends do I look at here? What numbers are important? What should I be looking at? Is my plant in danger? Is it about to fall over? You know, I don't know. So imagine this is the face that most operators will have upon looking at this sort of data. And so our contention is that all of this information is really of no use unless you have someone there who can do the interpretation for you, tell you what's important, what trends to look at, what to do, what to change, what actions to take. And so, for example, in the first place, we were approached by a client who had been receiving this sort of information for months, and their plant had fallen over. They were making no gas. We get their historical data, which is in yellow here. You'll see if you work in AD, you will notice there's very clear signs of instability. For example, phosphatic ratios up at whole positive numbers 7, which is quite bad, obviously. We then take over the managed service. The tank was heading for a crash at this point, so we couldn't do anything about that immediately. But then we were optimizing their strategies for recovery, lime dosing, feedstock optimization, as Wade was talking about, feeding rate strategies, telling them to watch their phosphatacs. And basically, we were eventually able to get them back down to full normal functionality. And you can see here, the blue area on the right is the long-term stability that this plant has enjoyed since they've been on the managed service. The next is the only example of any tank that we have managed service on ever having acidified. Essentially, the tank was taken offline for degritting and mixer repair. And they were given a dodgy dose of inoculum, essentially, that wasn't vetted. They put it in, tank acidified. As soon as this happens, we're on site the next day, and we don't leave site for the next 3 weeks. We're taking pHs, doing phosphates, we're advising on lime dosing and feeding, doing full feedstock characterizations, mass balances informed by those characterizations, and eventually we get the plant back to full capacity. And again, he has enjoyed a very long period of stability as a result. So, as I was saying, it's our lab that does the analysis. Then that analysis comes to us. We do the full interpretation of those results, and then we give actionable data to the client. And for both sites, this is typically what their engines look like. They have a 0.5 meg output, and they're pretty much always at full output capacity. And the ongoing weekly analysis, as Mal was describing, our dashboard system, will have a dashboard out to you weekly based on your weekly lab analysis, which will help steer you away from any kind of plant acidification event. Now, the next two case studies focus on dual stage digestion. First is a bench scale test, and the second is a full industrial tank conversion. So the first pilot scale study focuses on two technologies, which I'll briefly run through the outline of. I'm sure most people know this already, but for those who don't, anaerobic digestion occurs through four main stages: hydrolysis to acetogenesis, and then methanogenesis. In a single stage tank, all of these stages occur simultaneously, which is fine. It works for almost every plant, but it causes compromises. The products of these stages can interfere with each other and inhibit each other. So the idea of dual stage is simply to separate these stages. In the first tank, hydrolysis, acetogenesis, and acetogenesis, and then take the product of these hydrolysis or dark fermentation tanks and put them directly into methanogenesis tanks, where there is pretty much just methanogenesis and some limited acetogenesis. And this has the benefit of protecting the methane tanks and greatly enhancing the efficiency of the feedstock breakdown in the hydrolysis tank. So this is a typical web of interactions for anaerobic digestion. The broad groups and all the intermediates that feedstocks go through to become methane. So if you look at this graph, you'll see things like ethanol, long chain fatty acids, VFAs, long chain VFAs. All of these can be inhibitory on methanogenesis. And so the idea of dual stage is separate this from this very broadly. So that's what we do, and we do this via pH and temperature control in the first tank. The second technology is cavitation. So it's essentially a technology that takes rapid pressure changes in fluids to create microscopic bubbles that collapse upon themselves, releasing a huge amount of energy. This causes a breakdown in tough lignocellulosic feedstocks in particular, but it has benefits for all feedstocks really. But lignocellulosic is where you'll see the breaking down of the lignin, the cellulose, these things that sort of lock away a lot of the volatile solids in a feedstock. And so you get more from your existing feedstocks with cavitation, is our contention. Also, better activation area for the hydrolytic enzymes and hydrolysis, improved pumpability, as a result, makes otherwise tough materials digestible and increases the amount of feed you can actually put through the system. So for this bench trial, there was 4 60-liter tank setups. The first single stage control, no different from any typical tank, no pretreatment, no dual stage. The second, cavitation feedstock alone, so feedstock cavitated, put into a single stage tank, as is typical. Dual stage was both technologies, hydrolysis and cavitation. So the feed was first cavitated, then put into a hydrolysis tank, retained there, and then fed into the methane tank. So objectives of this work were to maximize the yield per gram of VS of this feedstock, improve methane productivity, and improve gas quality, i.e. reducing hydrogen sulfide improving methane content and hydrogen gas from the fermentation stage. And again, probably one of the more interesting things was the work we got to do on loading rates, which are very interesting. So hydrolysis tank, we simply set it up with a hydrolytic inoculum that we have generated through progressive runs at hydrolytic experiments that we think maximizes microbial activity. To this, cavitated feedstock was added. The temperature in the tank was dropped. The pH in the tank was dropped. The temperature was increased to maximize hydrolysis. Hydrolysate from this tank was, after a retention time in this tank, fed to the methane tank. Methane tanks seeded with a typical agricultural inoculum, and gas was measured via BPC unit. And we took all these typical tank stability measurements: pH, COD, TSVS, VFA accumulation. And the yield results, first of all, are quite clear. There's no real ambiguity about the effects of these two technologies. Single stage control, the feedstock didn't quite make it above 250 cubic meters per ton of VS. With cavitation, a significant increase to 290. And then with both technologies, quite a bit north of 350 on a good day. So that's 33% more yield compared to single stage, as you can see here. And if you look at this graph, the 7-day average yield in orange is where we are working on increasing the loading rate through the system. And then in yellow beside it, where we're working to maximize the yield per gram of VS from the system. And this will become important in a second. So a quick run through organic loading rate, I'm sure everyone knows, but it's essentially it's kilograms per meter cubed of volatile solids added per day, or grams per liter. Typically, the safe loading rate almost everyone uses is around 3.3 grams a day per liter, considered safe. Going above this can cause acidification and eventually for the tank to fail. Initially reducing your yield, and then eventually your tank will fail. So if you see on the left here, it's a typical graph, organic loading rate versus yield. And you see a very sharp drop off after the 3 kilogram per meter cubed value, as is quite normal. Some systems can work with up to 5 with a very good feedstock, but it's not rare. It is rare, rather. However, our contention is, if it was possible to push this value up, if you were able to push up organic loading rate without seeing a significant drop in yield, you'll be able to get a lot more gas out of the exact same tank space. And we've seen this is possible with dual stage. So this is our work on the loading rate for the third tank in the top left graph. We have FOSTAC versus OLR. FOSTAC is an intermediate value for tank stability, essentially. It's organic acids balanced against inorganic carbon, the buffering capacity of the tank. And so if you see the values that we got as we were really ramping up the OLR, didn't vary very much. So never above 0.3, always between 0.2 and 0.3, which is exactly where you want your FOSTAC. So all the way up to 9.8 grams a liter, our dual stage system was stable. Whereas in the single stage, the tank failed at around 4 grams a liter. And with cavitation, a significant increase, but still failed after 5 grams a liter. So as a result of this, we were able to get double the amount of gas out of the same tank space. And I think there's huge implications for this, of course. No need to build an extra tank. We can just fire a lot more feed through the same tank after hydrolysis. And if you look at this graph, as we're pumping up the organic loading rate, we're seeing no significant drop off in yield. That green line is our yield values for the tank that we are pushing the OLR up as far as we can. And in fact, we only stopped at 10 because we were running out of the feedstock. We probably could have gone significantly higher. So that's why we have these sort of tentative values of at least 2 times as much gas. We don't know where the ceiling on this is really. You could get significantly more. Other operational benefits: improved flowability after hydrolysis. The original feedstock is here. It's a difficult thick straw material that forms a very paste-like substance when mixed with water. It's very difficult to pump, to move around, to feed. And as you see, post-hydrolysis, you're seeing much more of a flowable liquid. And then the digestate is a fully pourable liquid. And if you saw the original feedstock that went into the system, you would know just how impressive getting this thing to pour it really is. So after a retention time of 29 days, including the retention time of the hydrolysis tank, you can expect to see almost full realization of VS to methane from this system, as we also say that this can greatly reduce your retention time as well. You get more quicker gas, you get it faster, it's better quality. It's all positives. Other operational benefits, we didn't actually really think that we didn't expect to see this, but hydrogen sulfide control, because we could control the pH much more effectively in both tanks, we were actually able to keep them outside of the optimum range for sulfidogenic bacteria. So in the hydrolysis tank, it's below 6.5, and then we find naturally methanogenic tanks fed hydrolysate will sit around 8.1, 8.2, and this is outside the comfort zone for the bugs that make hydrogen sulfide. So we've seen values below 100 parts per million and typically in the 20 to 30 range for hydrogen sulfide. Another benefit, the hydrogen generation from the fermentation tank, from the hydrolysis tank, typically in the range of 30 to 40%. And this hydrogen gas is valuable. You can either filter it, sell it, or probably more realistic use of it is biogas upgrading on site. At these percentages, hydrogen can be used to bubble through your methane tank, and ideally it will give you a boost in methane quality of 5 to 10%. That combined with the increased methane quality from dual stage and cavitation, I mean, you're looking at really great numbers for CH4 quality. So summary of this pilot scale trial. We found OLR capacity is, we haven't found the ceiling for it yet. We more than doubled what we got out of the single stage, 9.8 grams a liter. Theoretically, we can be getting, we were getting double the biogas, and theoretically we could get even more than that if we were to push it further. Tough feedstocks become digestible. Methane quality increases with cavitation and then further with both technologies. Process stability as you're separating VFA-induced crash risk from the methane tank, and considerably lower hydrogen sulfide generation, and also hydrogen co-production, which can be used for biogas upgrading. And so next case study, last case study, is the actual tank conversion that we've done on a full-scale industrial site. So the objective here, what the client wanted essentially was the hydrolysis benefits for reducing feedstock use, as they don't really have the capacity at the moment to use extra methane. So what they want is CapEx reduction. So to do this, we converted an existing on-site tank into a dedicated hydrolysis tank. And we did this pH adjustment, temperature adjustment, volume adjustment, and with the addition of our own bespoke hydrolytic inoculum. So reduce the pH, we used acid and iron dosing, volume changes, increasing the heating profile. We did this in a very careful stepwise fashion to avoid washout or sterilization of the tank as it exists. And then the other part was to generate our own seed inoculum. So we made 20 tons of hydrolytic inoculum in our biological plant up in Ballymena. We did this by taking slight digestate, enriching it with synthetic nutrients, and tailored microbial groups to boost hydrolysis. We then put this into our biological system for at the ideal temperature, pH, and retention time to maximize activity and really make the most dense biological community we could. So what is this inoculum? It's a dense microbial community enriched with hydrolytic, acetogenic bugs. We think it gives you a much better maximum tank efficiency, higher ceiling for acid production than you would get without it, faster breakdown of your solids, higher VFA production, and improved downstream methane generation compared to a tank without it. As I said, you produce it by adjusting pH, nutrient ratios, temperature, retention time, and made it in our own facility. Stored in IBCs, ready for transport in either truck or IBC format, whatever one would prefer. Results, significant increase in methane quality from 53 to 60%. Engines have maintained near 100% utilization for the entire time after the conversion of this tank. And if you look at the bottom right here, you'll see start of the project. This is when it is still a methane tank. There's very low VFA accumulation. As we start changing the pH and the temperature, you see acid accumulating up to the point where it sort of stabilizes out and stops. Then we add our hydrolysis inoculum, which we see a doubling of VFA content, and then eventually, more recently, a tripling. So the values of VFAs we're getting are really, really, really high. This is a lab report from a recent sample. As you can see, we're getting really, really big numbers, 22 grams a liter of VFAs. And that is excluding longer chain VFAs like caproic acid, as we only currently test up to carbon chain length 5, but almost certainly we're getting significant caproic acid in here and lactic acid. And there's a value in this outside of the context of just VFAs being food for methanogens. Butyric acid, for example, which we have 15 grams of per liter here, is valuable in the manufacture of bioplastics. Caproic acid, which is almost certainly there in quite a volume, is a valuable ingredient in the cosmetic industry. Just doing a quick look around, can sell for more than 3,000 pounds a ton. So we're thinking this could be another eventual value add of a hydrolysis tank. Another benefit, of course, he's getting the feedstock reduction due to better VS utilization due to the dual stage technology. So that's a 30% decrease in operating cost. Another thing we didn't expect, the hydrolysis tank is hotter and pumps forward a heated hydrolysate into the methane tanks, but it's only 10% of the volume of the plant. But because of this higher temperature and the natural thermogenic nature of methanogenesis, he doesn't need to heat these tanks anymore. The heaters are off in these tanks. There's one tank that's heated and everything flows from there. So summary of the benefits: higher gas quality, more gas, stable output, lower feedstock, reduced hydrogen sulfide. As you can see there, that's from on-site data from recently. Before tank acclimatization and after these tanks are fed hydrolysate, you'll see that the H2S really just goes off a cliff. So less cleaning you need to do on your gas, less you need to replace your filters. And again, greater utilization of this feedstock results in lower residual biogas potential in the feed, which is great for anyone with PAT 110 concerns or the like. Also, he has the capacity now to use this hydrogen gas for biogas upgrading, should he so wish. And also, as we discussed in the pilot scale trial, if you wanted to massively increase the OLR through this system and create a lot more gas, if and when he gets the capacity to do so. So summary of the two stages, the cavitation and dual stage rather. Better methane yield, greater stability, much higher capacity for OLRs and loading through the system, greater gas quality, higher methane, lower hydrogen sulfide, operational savings on feedstocks, less mixture stress, better pumpability, less heating. Very easy to implement this at a very low risk, as it can be a converted existing tank or a much smaller tank that can be built and then doesn't work. You can convert it back, but we think it absolutely will work. Cavitation supports hydrolysis as it opens fibers up to more enzymatic activity from bugs, improve flowability for that feedstock, again, enhanced methane potential, and supports the higher loading rate of dual stage. And yeah, that's all the case studies. If anyone has any questions, please send them through and we'll address them as soon as we can.
Thanks very much, Dara, for your presentation. It's very interesting. Probably a lot more technical than we've had on previous webinars, but it's great to get the information and to understand the developments and the innovations that you're pursuing. We have a number of questions coming in. I would encourage anyone, I know one or two raised their hand, but we just don't have a mechanism to bring you in person. You need to, or we ask you that you actually submit your questions via the Q&A tab. We want to bring in, or it's not possible to bring in people to ask their questions in person. So just before, if I could get, just before we get to the questions, let's maybe just a couple of points, if we could go back on that you've highlighted during the course of your presentation. Can you just maybe outline again the importance? You very clearly stressed at the start, I think it was Mile at the start, and it's a question as well here about the importance of a science-first approach. Can you just explain that again, if you don't mind, please? Mile or Dara that mentioned that?
Yeah, I mean, I suppose from our point of view, I guess one of the, and like you don't want to, we've approached this very much from the point of view of understanding what's going into the AD plant, how the AD plant is performing, and what's coming out of the AD plant, Sean, ultimately at the end. And we're aware that there's products available in the marketplace that claim to boost X, Y, Z, and there's almost sometimes there's a belief that well, throw it in and see what happens. And really, our approach is quite different to some. And what we say is, well, let's pay for the correct analysis. Let's understand what the science tells us, and then respond accordingly. And Wade's point at the start, which is it's ultimately we talk about a concrete stomach or a steel stomach, whatever it might be, but it is a stomach regardless. And understanding the nature, the quality of what you're feeding that stomach is absolutely vital. And there have been instances where we've been asked to analyze the digestate from a site and then help them figure out what's going wrong. Inevitably, we try to say, well, look, we have to understand what you're feeding first, Sean, because you're only seeing one side of the story. When you analyze the digestate, you can see something going wrong. You can't necessarily determine from that what it is that's driving these inhibitory elements that are present. So quite often, from analyzing the digestate, you'll say, aha, we see signs of inhibition. We see signs of something unhealthy in here. Inevitably, though, then you have to go back to the diet and then say, right, where is this? It may be a single source of problem, or it could just be the balance, the recipe. So inevitably, that's why we talk about this science-first approach, which is let's understand, is the AD biology happy, content, stable? If so, great. What can we do to help the site, become even more viable? Can we reduce the feed, or can we get more out? Or if there's something that's holding the site back from, destructing as much volatile solids, what can we do then at the front end to mitigate any of those imbalances?
Okay, thanks for that. Just to follow on, I think it was Wade, if I could bring Wade in, you mentioned about the importance of full feedstock characterization. Have you noticed significant variations across the same feedstocks in terms of that characterization? Because I know that members would have explained that to us, and we would have seen it ourselves in some pieces of work we're involved in, that you can get significant variations in biomethane potential across the same feedstocks, even in the same farms. But just what's your experience around that? I know your characterization is a lot broader than that, but can you just give us an outline of the variations you see, and is there much variation across the same feedstocks?
The short answer to that is absolutely, Sean. The variations across all feedstocks, whether it be a commercial food waste, an agricultural product, or anything like that, the variations are massive. You can. Commercial food waste is obviously going to vary because of seasons and the difference, whether it's Easter, whether it's Christmas. You've obviously got a big variation in that. Agricultural crops residues will vary as well, because they are subjected to any kind of environmental issue, whether it could be drought stress, rain stress, could be nutrient supply, could be soil, could be, there's so many different, harvesting times are huge. I've seen such a big, and I've done a lot of work in Northern Ireland with grass, and grass can vary from week to week almost in terms of its carbon, nitrogen.
In terms of slurries and manures, is what's because
I think,
that's a big focus on those in terms of feedstocks.
Yeah, I think slurries and manures are less susceptible to change because they've gone through their own biological rumen system. So there's almost like a chelated nutrient supply at the back. So it's less, but it is always determined by what the cow or the pig or whatever it might be eating at the time. But it is less prone to any kind of change. But it does change. It does change because of the feedstock coming in.
A question here is, and I don't know which of you wants to take it. I suppose, how can or what influence does your work have on, say, policy, in terms of how can your work influence, like a lot of the work of the Irish Bioenergy Association is around policy development, support mechanisms, frameworks, regulatory items. So I suppose, have you any suggestions as to how your work and the findings of your work could influence that policy development, and are there items that need to be considered now to make what you're doing more of a reality on more sites?
It's an interesting one, Sean. I suppose from our perspective, I think it can support the operators to add value to the next stage of nutrient management. I think it probably is fairly critical. I mean, there's two big things we think this technology can do. One is it can significantly reduce the capex required to produce biomethane. So you can produce an awful lot more gas through a smaller footprint, which makes it more viable for the operator, and should allow us to fulfill, the targets faster with lower capex if it were to be fully deployed. But ultimately, we see the pressures up here in the north, and they will follow suit elsewhere around nutrient management. And I think AD is seen as an important part of the puzzle to help manage and mitigate certainly phosphorus. And the way that'll work is really, you're consolidating phosphorus off the field into a tank. But once it's in the tank, it'll still come out. It'll still come out in the digestate. But if you're ultimately producing significantly more energy, the potential to produce significantly more heat, you have the ability then to extract or concentrate that phosphorus. Ultimately, in the north, we're talking about exporting it. But if you have a plant that's more able to push more product, more feedstock through, it can take more phosphorus off the land, and it's producing an awful lot more heat and power, then it has a much greater capability to be part of the puzzle for exporting phosphorus from the island.
Okay, there's a couple of quite technical questions. So first question from Shane: what's the retention time and temperature required in the hydrolysis stage? So we'll hopefully get through these quite quickly. So retention time and temperature required in the hydrolysis stage.
Dependent. Is we would, I suppose, what we would prefer to do is work with, if there was very specific questions around ultimately your retention is significantly lower and the temperature is reasonably higher. But it would be wrong of us to glibly state a retention time and a temperature, because it can be a bit more nuanced than that. But if there's ever specifically wanted to discuss, a very specific aspect or element of that, we'd happily have that conversation offline, Sean. But I wouldn't want to give advice out there without being more mindful of what it is for.
Question from Lucy: have you carried out any energy balance on the two processes?
Yes. If we're talking about cavitation, it's a very, very low consumer of energy, proportional to other, which is why we like it. I mean, we have no real vested interest in cavitation, other than we see it as a low energy means for opening up those volatiles for destruction. but we're not closed to other means of mechanical breakdown. But we find the hydrodynamic cavitation very cost effective. In terms of mass balance, I mean that the industrial site that we're talking about there is producing 30% more gas on 30% less feedstock. So the energy balance is massively net positive.
Have you any experience of AD of sewage sludge waste and any learnings of that particular feedstock?
Yes, we've done studies for 2 UK municipals on sewage sludge digestion at pilot scale. We've been involved in pilot scale trials with these 2 UK municipals looking at cavitation plus the hydrolysis stage. Both obviously have very similar to what we've seen on those IrBEA feedstocks. A very similar step. Cavitation provides 10%-ish improvement. The coupling of
you'd be able to give specific feedback to Gareth if he wants to get in touch with you there on the sewage sludge if he has a query on it.
Yeah, for sure.
Lucy again, what are the feedstocks on the industrial site?
Typical agri waste.
Agri waste stuff, brewery waste, some sugary waste, lactose and ryegrass. It's a real small waste board.
Chicken
litter. Yeah, everything on it really.
Another question there. Have you done any dry matter balance on the use of straw? Are you needing to add liquid?
Oh yeah, we add liquid. I mean, it's not just pure straw. There's a feedstock mix and ratio we have. Okay. But yeah, no, we have done that.
Okay. Question from Marcus. You mentioned cavitation as an approach. Have you investigated any other forms of mechanical pre-treatment, such as steam or ultrasonics?
Yes, and find cavitation preferable from our point of view. Yeah. Certainly, yeah. More reliable, less cost effective, or more cost effective, less Todex, as it were.
Okay, the questions are flying in at this stage, so we'll try and go through them fairly quickly. We might run over by a minute or two. Please, and you might have covered this, but just a question from Mark. Please recap what the feedstocks were in each experiment and case study. So I think you have mentioned it for the industrial site, but do you want to?
Oh, sure.
It's a straw bedding material in the pilot.
With a mix of some animal manures.
Yeah.
Oh, okay. The next one is from what will the process look like to collaborate with Clinty Bio from receipt of a new organic byproduct to a full feedstocks analysis and recommendation of suitable processing routes? So this person is highlighting this and giving our role in sourcing and assessing organic byproducts for our clients to find suitable outlets for disposal. So the best process looks like to collaborate with yourselves.
I suppose. And I guess what I should say is we have a facility up here in Belfast, which is right in the docks. We're happy to bring people up and take them around. And what you'll see up here is you have the laboratory, and right next to it you have an engineering space. And we have, I think, fairly unique capability to run both continuous pilot studies. So we can run sort of probably 4, 5, 6 lanes of continuous pilots through these 60-liter tanks. But we also have the ability to, because part of our other business is water treatment, waste treatment. So we have a great ability to understand the chemical processes involved as well. So we have chemical engineers and biological engineers. So we can take any particular product through dewatering, understand what the steps are to maximize dewatering, and understand how best to valorize any particular waste, whether that's pre-digestion or post-digestion.
Okay.
But if anybody wanted to come and see, drop us a note and we can arrange a
get in touch with you there and talk about that further. Next question: what are your target HRT and SRT distributions for the separate hydrolysis, acidogenesis, and metagenesis tanks, and how do you determine the optimal HRT ranges for each phase? So,
yeah.
I don't know, can that be answered in a 30-second answer?
Yeah, sorry. Again, that'll depend. Say for lignocellulosic feedstocks, typically you want a retention time of, say, 7 days. That's just out of the papers. For other feedstocks that are easy to break down, you'd want less.
Okay.
That's how that's determined. And then the feeding rate out of those tanks is decided. We will do like full VFA analysis on that hydrolysate to see when it's sort of reached its optimum production period.
What could be done on a single tank system, AD system, with farm waste and grass in terms of your own work?
Well, as in, we would advise the cavitation really shows its biggest benefits with agri waste and farm waste like that. So if you're just doing single stage cavitation, will almost certainly be a benefit to you.
Okay. And again, next question. We might have covered it. For most plants are now backed by large investors who need guarantee, etc. from AD technology providers. Can you see hydrolysis getting the guarantees and ultimately passing the due diligence for financing of new builds?
Yeah, that's an interesting challenge for sure. And I guess, you know, potentially the reason why hydrolysis hasn't got more traction to date is that when it needs to come with a process control, it doesn't suit the big technology providers to, you know, put smaller tanks in. It maybe suits to put in larger tanks. But what we've done is work with the sites that don't require process control and are self-funding or self-financing. If it's one of these large groups that requires red line process controls, I think we've got significant interest from a number of the large manufacturers who want to collaborate and trial. That they won't yet offer process controls until they've run their own studies on it. But like I say, the risk is so low because the required capex is so low that it de-risks itself.
Okay, we've just one or two questions more. We might do them, but it's going to delay us maybe a minute or two more. So, what process design measures are used to minimize foaming, solids carryover, and short circuiting between the phases?
Well, we haven't seen much in the way of foaming in any of our tanks. I mean, feedstocks we would use, like say fatty feeds, we haven't really used, but I mean that will be typical in any tank system. We don't see any overloading really, as we were talking about in the OLR work. The feed forward hydrolysate is very stable. In fact, we didn't find the point where it became unstable.
Okay. Another question here. You mentioned reduction in HRT. What was the initial stroke final HRT, and how was the split between the two tanks?
Initial one stage was around 47 days, and then dual stage it was 29 days.
Okay. Similar question, but separate. What could be the average necessary retention time in the metagenesis tanks, and would the capacity from this tank maybe 2 or 3 times bigger than the hydrolysis tank?
Yeah, sorry, the size of the hydrolysis tank is significantly smaller. Again, it varies by feedstock, but the footprint for the hydrolysis tank is like it can usually be about 1/7 the size of the methane tank that it's feeding. The retention time is much lower in hydrolysis, so it can feed forward into a much bigger tank.
Okay. What organic loading rates do you design for in each phase, and how do you prevent overloading of the hydrolysis tank or acid shock in the metagenic tank? How do you control VFA and accumulation and pH stability in the acidinic tank to avoid downstream inhibition in the metagenic reactor? It's a fairly technical question.
Yeah, to say it, yeah.
Yes, if you want, we can get O'Doul to contact you directly, maybe, and talk further.
Yeah, sure. I think we addressed a bit of that, but essentially the feed forward, the VFAs come out of the tank. The downstream methane tanks can adapt quite quickly to much higher VFA content from the hydrolysis tank, and initially loading into the hydrolysis tank, it sort of pH controls itself. It keeps itself in a nice band of consistent pH. It doesn't overload the system. We don't see overloading or much need for pH control. Feeding controls the pH.
Okay. Second last question. How would you recommend hydrolysis for high nitrogen AD, such as poultry litter, monodigestion?
Yes. Poultry digestion on itself is always difficult. But yeah, hydrolysis should help. I think with ammonia inhibition, you can control the pH in both tanks a lot better, and as a result, you can kind of keep the free ammonia fraction a bit lower in both tanks. So it could help with that.
I suppose the important thing is we don't necessarily have every answer to every question. What we do have is a set of pilot rigs, so we can run if there was a very specific sort of very nichey kind of feedstock or system, we have the ability to replicate it. So you can run one lane as a control, what the site currently does, and then you can run lanes 2 or 3 or 4, whatever you might want, as different variables or different variations on that to understand, what is the impact of dual stage, what would the impact be of just cavitation, or what would, or even if somebody came to us and said, well, I'm very interested in this other pre-treatment technology. We've run trials in the past where we've been given a protocol to an extent, and we've fulfilled that protocol on behalf of a client where we haven't said we believe this is necessarily the best technology or process. So it can be run as an independent test center as well.
Okay, how does it work with farm? It's a question here. How does it work with on-farm waste and grass systems?
Probably better than with dry straw. Fresh cut silage would almost certainly be preferable to work through the cavitator and then through the dual stage system than dry straw.
Final question from Christopher. What do you do with the dark fermentation gases?
Well, that's the thing. What we want to do is use it for biogas upgrading. Currently, we're trying to work out our own rig here in Dorgan to get that fermentation gas and get it bubbling through the fermentation tanks, through the methane tanks. That is ultimately the goal, because all the research suggests that 30 to 40% hydrogen mix will give you a significant boost in your CH4.
Ultimately, use it as a gas mix in your methane tank, Sean.
Yeah.
Very good. Okay, we've come to the end. I think we've covered 95 or 99% of the questions. Hopefully we haven't missed any. We had a huge attendance this morning, very good engagement. So I thank all our speakers. So thanks to Mile, thanks to Dara and to Wade. I also thank all our attendees this morning for registering and participating. We hope to see you back on a future webinar. And just to conclude, to say that this webinar has been recorded and it will be available on our YouTube channel in the coming, probably be early next week at this stage. And finally, just to say, if you have, well, there was a lot of technical questions there. If you have any specific questions that you'd like to ask, you can see the email address there on screen, sales@clintybio.co.uk, and a phone number as well, and their web address. So please get in touch with the guys in Clinty Bio, and I'm sure they'll be happy to provide some information and potentially solutions to you if you're in the AD sector. That's it. Thanks very much, everyone. We'll leave it at that, and we'll conclude this morning's webinar. Until the next time, take care and see you again soon.
Thank you, Sean.
Bye.
Thanks, Sean.